Hey, and welcome back. So we're going to kind of goof around with the rate law here a little bit, just kind of play and learn some of the details here, and we'll just kind of look at the units of things as well. So for instance, here's a chemical equation, and we looked at this in the last lecture, and we've got an experimental rate law. And if you notice, those coefficients in the equation there are definitely not the same as those orders, those powers in the rate law. So they can be, or they may not be. So we have to experimentally determine these. So let's see what, we might do with this information. So imagine we know the concentration of hydrogen in an experiment, right, is 0.010 moles per liter. And the concentration of NO in an experiment is, say, 0.0025 moles per liter. Then if we knew the rate constant, we could actually use this equation here to predict the rate. But actually, let's go backwards. Let's say we know the rate of the reaction. So maybe we've got the rate of the reaction. So normally we wouldn't be doing it this way, but why not, right? We're goofing around, and it's 3.5 times 10 to the minus 6 molarity per second. We can ask a couple of questions. So question one might be, what is the rate constant? And question two might be, if we change those concentrations, so if we do another experiment where we make the hydrogen and NO concentration exactly the same, maybe half a mole per liter, what will the rate be? So that's really awesome, right? To be able to predict the future. What will the rate of this new experiment be? So answer one, so we're going to go ahead and we're just going to rearrange our rate law expression. So if we want K, we can set that equal to rate divided by h2 to the first power. I'm not going to write that number 1 in, times by NO to the second power. I guess I got to write that in. So we were told the rate in this problem of 3.5 times 10 to the minus 6 molarity per second. All right, what do we have on the bottom? We got the concentration of hydrogen, 0.010 moles per liter. We've got the concentration of NO, and I'm going to put it in parentheses because I'm going to be squaring this. I want to make sure I do this and keep track of units correct. So it's 0.0025 squared. And I can go ahead and I can type that in on my calculator. And on my calculator, I get 56. Now, in terms of the units are kind of nifty. So if I look at the bottom, I've got molarity, and I've got molarity, but I got to remember that I'm actually squaring it. So that's molarity times molarity squared, so that is molarity cubed. And on the top right, I haven't done anything, so it's molarity per second. So I've got molarity per second divided by molarity cubed. What can I do with that? Well, molarity on the top will cancel with one of the molarities on the bottom, so it will leave me with molarity squared there. So my units are going to be 1 over second divided by molar squared. And actually, I can just put the second down the bottom, so I can also write that as 1 over molar squared second. And actually, that's kind of ugly, isn't it? So I can write that as 56. So 1 over molar squared second, that would be molar to the minus 2, seconds to the minus 1. So that would be one way to write the rate constant. So let's move around with the second part here. So let's go ahead and move the screen. I always struggle with this bit. I'm sorry. There we go. I just need a little bit of extra room there. Okay, perfect. So now I'm going to go ahead and I'm going to calculate the rate. So I'm going to really use the predictive power of the rate law here. So I'm going to take advantage of the fact that the rate law lets me predict the future. And that's really what science is all about. So I know the rate is equal to K times by the concentration of hydrogen times by the concentration of NO all squared. K is my rate constant, so I've calculated it to be 56, let's see, molar to the minus 2, seconds to the minus 1. And I'm going to multiply that by hydrogen, and it is 0.5 molar in my problem. And I'm going to multiply it by the concentration of NO. So again, that's 0.5 molar, but I am squaring that. So in terms of the number part of it, I can type this in on my calculator, and I get something like 7.0, I think. And but in terms of the units, what are the units going to be? So the molar to the minus 2 are going to cancel with the molar that I am squaring here, and that leaves behind molar, and it leaves behind per second. So my units are going to be per molar, are going to be molar per second, right, or molar second to the -1. And does that make sense? Well, the rate of a reaction is the rate of change of concentration with time. So concentration would be molarity, time would be second. So if I divide molarity by time, right, or concentration by time, I should get molarity per second. So perfect. So that makes total sense to me. And therein lies the beauty of chemical kinetics, right? So we can make predictions as to the future. So we can run this reaction under completely different conditions, completely different concentrations, I should say, and we know exactly how fast it will react. So that, to me, is gorgeous. Thanks.